Let's talk about conditional probability and independence. The probability that one event happens given that another event is known to have happened is called a conditional probability. The key word there being given that another event is known to have happened. The conditional probability that event A happens given that event B has happened is denoted by what you are seeing right here, the probability of A given event B. That line right between the A and the B represents the word given. And what you can see right below in the formula that is in this rectangle is the basic relationship of a conditional probability to the intersection of those two events. If you have the probability of A given B, that is solved by taking the formula of the probability of events A and B happening at the same time, their intersection, which is the upside down U symbol you see right there. The intersection of those two events would be in the numerator, and then the probability of event B would happen in the denominator. You would divide those two events, and that would give you the probability of A given event B. And the same idea goes if you were to flip-flop the positions of A and B, the probability of event B given event A, just notice how event A is in the denominator, and still the intersection of the two events would go in the numerator. Let's look at an example. In the 2016 Summer Olympics, the United States and China won the most medals. Suppose we are randomly going to select a medal from the 191 that are represented in the two-way table. To find the events, gold as G, U, the United States, and B, bronze. Go ahead and pause the video if you want to try it on your own, but here are the solutions. In part A, we are finding the probability of event B given event U has taken place. That means the probability of getting a bronze medal given that the United States won a medal. So you will notice right over here in red, the probability of the United States winning a medal. There were 121 medals won by the United States, so 121 is in the denominator. The probability of getting a bronze medal is 38 of those 121 medals were bronze, so you would just do 38 over 121. The intersection of bronze and the United States was the number 38. So back on the previous slide where you have that numerator, the intersection of the two events, that is found by just taking the 38 where United States and bronze, that row and column meet. The context of this statement, given that the U.S. won an Olympic medal, the probability that the medal was bronze is about 31.4%. That is just taking the percentage from the decimal version of it right there. Part B, given that the chosen medal was not a gold medal, what's the probability that it came from the United States? So not a gold medal means you are excluding the gold column. So that means you need to look at the medals that were won by the United States that were not gold. And that would be we have 37 of them were silver and 38 of them were bronze. So those are the medals that are not gold won by the U.S. And you can see right here at the bottom, adding those two values together gets you 75. And then the denominator is the total number of medals that were won that were silver or bronze. Because notice the statement that we're looking at right here. Given that the chosen medal is not gold, it doesn't say what country won the medal. It just says that the chosen medal, the total number of medals, is not a gold medal. So that means you would exclude the 72 medals that were gold, and you would just add up the 55 and the 64 representing the medals won by the U.S. and China that were not gold. So right over here in the bottom corner, you have the 55 plus 64 giving you 119, and then the U.S. won a total of 75 of the 119 medals that were not gold, and that would be about a 63% chance. Writing this as a probability statement, you can see that right here at the bottom. Given that the medal was not gold, you're going to notice the complement symbol right here. Let's just go ahead and rewrite it. The little c that looks like an exponent, that means the word complement, which means the event does not occur. So it said the medal was not gold. So you can denote that by putting a G with a little c in the upper exponent kind of region of it. And then that vertical bar means the word given regarding this problem. So given that the medal was not gold, that's the part that is on the right side of the vertical bar. What is the probability that the medal came from the United States? That is why a U is on the left-hand side. Here's another problem. According to a recent report, Apple Music and Spotify are the most used music streaming apps. A group of AP students surveyed all the seniors at a school and found that 68% use Apple Music, 38% use Spotify, and 24% use both. Suppose we select a senior at random. Given that the person uses Apple Music, there's that key word. Given that they're using Apple Music, what's the probability that they use Spotify? And here is the answer. So this goes back to the formula on 2 slides ago. The probability of two events where they are conditional is where you take the probability of their intersection and you put that in the numerator. 24% of the people use both Apple Music and Spotify, so 24 goes in the numerator. And then the denominator is just the overall probability of the given event. You would divide by the likelihood that they are using Apple Music in this case, which was 68% of the people. So 68 goes in the denominator, divide these two values, and you get 35.3%. A and B are independent events if knowing whether or not one event has occurred does not change the probability that the other event will happen. Knowing one event does not change the probability of the other event. That is what independents mean. They are not relying on one another. In other words, events A and B are independent if the conditional probability of A given B is the same answer if you did the conditional probability of A given that B does not occur, which sounds probably incredibly convoluted, but you can see the formula right there. You get the same result of what I'm highlighting in purple if the events are independent. It doesn't matter what the complement is in the situation, the events are independent. Likewise, events A and B are independent if the probability of event B given event A gives you the result of event B. So for example, it's going to make a lot more sense when you can see an instance of this happening. Let's say we are looking at the probability of, or actually let's just get the other writing on here. Let's look at the probability of getting a pierced ear given that the student was a male, and then the probability of a pierced ear given that the student was female. We are looking to see if the events of being pierced ears and male are independent. Look at the results. When we make the denominators the total number of males and females, 90 and 88, you can see those numbers right there. The amount of people with pierced ears, 19 of them were male, and 19 pierced ears people were male, and there were 90 males. So given that they were male, there was a 19 out of 90 chance that they would have pierced ears. Likewise, for females, there were 88 of them, and 84 of them had pierced ears. So when you do that fraction, 84 over 88, you get 0.579, which is different than the probability of having pierced ears given that they were male. Therefore, knowing that the chosen student is a male changes or reduce the probability that they had a pierced ear. These events are therefore not independent. The basic idea, if everything you just heard isn't exactly clicking, it is to understand that both events are not helping you predict the other event. You got the exact same probability. You got two different probabilities. 0.211 is not equal to 0.579. So therefore, these events are independent. If we got two results that were something like 0.33 and we also got 0.33, that means the events are independent. Let's take a look at an example. Is there a relationship between gender and subject preference being math or English? The two-way table summarizes the relationship between gender and subject preference for a class of 25 AP Statistics students. Suppose we choose one of the students at random. Are the events male and math independent? Here's the answer. So we start by doing our probability calculation. It's the events male and math, are they independent? So we are taking males as the denominator. The total number of males was 10, which you can see right there. And how many of them liked math? There were 8 of them that liked math. So 8 out of 10 gives us 0.8. We are seeing if male and math is independent from female and math. So the amount of female students that existed in this study was 15, and the amount of them that liked math were 12. 12 out of 15 is also 0.8. You get the exact same probability when you do liking math given that they were male or liking math given they were female. Therefore, yes, these two events are independent because their probabilities are exactly the same. It didn't matter what the gender of the student was. The probability that any student was going to like math was 80%, no matter what gender they were. So therefore, gender and math preference were independent events. They are not related to one another. One event is not helping you predict the other event because you get the same probability. And mathematically, that is what you would look for. The exact same fraction to decimal proportion. So likewise, if we had the numbers 1/2, and we also got the number 4 out of 8. Both of those fractions reduced to 0.5. Therefore, if you got two results that gave you those probabilities, then you would know the events were independent. So again, independent events have the exact same probability. So at the very least, you know what to look for. The two events will give you the same ratio if they are independent events. Tree diagrams and conditional probability. A tree diagram shows the sample space of a chance process involving multiple stages. The probability of each outcome is shown on the corresponding branch of a tree. All probabilities after the first stage are conditional probabilities. So by first stage, we mean the area right there that I just circled, and then the area that comes second would be a conditional probability. So here's what we're looking for here. There are multiple stages. You can see right here, for example, there is a 60% chance that a student is going to hit the snooze button. So that would be 0.60. And then if you're trying to find the probability that they hit the snooze button and then they're also on time, those two probabilities happening together, you would simply multiply 0.60 times 0.70. And that would be the probability that the student is on time given that they hit the snooze button. They are conditional. So as you string the probabilities together, you would need to multiply them. You would not just say, oh, the probability that they're on time given that they hit the snooze button is 0.70. That is not correct. 0.70 is only the probability that they are on time if they hit the snooze button, given that they hit the snooze button. So that would be 0.60 of them just hitting the snooze button, and then multiply that by 0.70. And that would be the probability statement that you are seeing up here, that I will back up all this purple. And it would be the probability right there, that they are on time given that they hit the snooze button. All the other probabilities work in the same way. Something to just also quickly notice, 0.6 plus 0.4 is going to add up to 1.00. And then the tree part right here, 0.9 plus 0.1 is also 1.00. Each branch of the tree diagram is supposed to add up to 1.00 because these are all conditional probabilities after some event happened first. Let's just look at an example of this basic idea. Who prefers pop music? In 2024, the age groups of Spotify users are as follows. I'm not going to read all of these off because we are about to fill in a bunch of business right here, so let me just skip down. You have multiple categories of users and the age groups given right there. And then it tells you you have separate percentages within those age groups for what their favorite music genre is going to be. The first question is going to ask you to draw a tree diagram to model this information, and you can see that tree diagram right here already set up, but the only thing we need to add to it are the percentages. So here's what all that looks like, and here's what the entire question is going to be. So, starting with the tree diagram, notice how it says 55% of its users are between 18 and 34. Here's 18 to 34, 55% of the users go on that branch of the tree diagram. Next, it says 27% are ages 35 to 54. You can see that percentage right there in the middle. Lastly, 19% are 55 and older. That would be the bottom category. If you add up those three numbers, you're going to get 1.00 or 100%. It then goes on to say, for the 18 to 34-year-olds, 64% of them liked pop music. So within the branch of 18 to 34, you are going to say 64% of them like pop music. Therefore, if you do 100% minus 64%, you are left with the 36% of people that do not like pop music. And that is how you fill out the rest of the branches of this tree diagram. Moving on, 53% of the 35 to 54-year-olds identified pop music, and that would be right here. So you would do 100% minus 53, and that would give you the 47. And then lastly, 37% of the 55 and old people like pop, so you would subtract 37 from 100% to get the 63 right there. All the probabilities on the individual tree branches add up to 100%, and then the initial branch of the tree diagram is also 100% of the data. Find the probability, part B, find the probability that the person identifies his or her favorite music as pop. We want the people who like pop music. That would be 1, 2, 3. In order to find these probabilities, you need to be careful. You are not just taking the 64, the 53, and the 37. Those are the probabilities given the age group. You have to multiply the probability of the individual being in the age bracket before you can multiply the probabilities that they like pop music. So notice how the math is set up. We take 55% chance that they're an 18 to 34-year-old. So that probability that they're within that age group is what starts the calculation. And then you multiply by the likelihood that somebody in that age group likes pop music, which would be 0.64. That probability is now going to be added to the next age bracket. There is a 27% chance that you get somebody who is 35 to 54, so there's the 0.27. And then the probability that somebody in that age group likes pop music is 53%, so you would multiply by 0.53. Repeat that process one more time for the last leg of the tree diagram. 19% of the 55 and ups like pop music, and you would multiply that by the probability that they like pop music, which was 0.37. The main thing to take away is that you multiply, I'm abbreviating it you multiply your events as you are doing one event after the other. They are conditional. You multiply the events together. Multiply, multiply, multiply. That is what you are doing to find these individual probabilities. You add them up after you have them all calculated, and you will get a 56% chance, or 0.56, that somebody likes pop music. Part C. Suppose the chosen person identifies their favorite music as pop. So given they like pop music, what's the probability they are ages 18 to 34? Given they like pop music, we just calculated that. That is the 0.5654, so that is the denominator. And then that they identified, or that they are part of the 18 to 34 group, there is a 55% chance that they are within that group, and then a 64% chance that they like pop music. So you would multiply those probabilities together, and that would be your numerator. Do all the math, and you get a 62.3% chance. 14. Lie detector suits. In 2012 interview with CBS News, Tom Hanks said that 80% of the population are really great, caring people who will help you and tell the truth. And I think 20% of the population are crooks and liars. So this is an assumption that we are getting. 80% of the people are great, 20% of the people are liars. A new lie detection suit has been tested and was shown to correctly identify truthful people 88.9% of the time and correctly identify liars 75.6% of the time. A positive test is one in which the person identifies as a liar. So if it's a positive test, they were a liar. A negative test test is somebody who is truthful, because it's a lie detector test, so it's looking for the liar. Sometimes the test suggests that a truthful person is a liar, which is called a false positive. Other times the test indicates that a liar is being truthful, that is a false negative. Assume that Tom Hanks and the company that makes the lie detector suit are telling the truth, that they are able to make these probabilities. A randomly selected person from the population tests positive for being a liar. Find the probability for this. Here is a tree diagram to help illustrate this point. Please listen as I explain where all of this information comes from. It starts with the first branch of the tree diagram. Tom Hanks, up in yellow up here, just an actor if you don't know who he is. 80% of the population are great people that are telling the truth. 20% are crooks and liars. So 80% of the people in this tree diagram are telling the truth. 20% are liars. And this is the assumption from Tom Hanks. We now have in the second part of the tree diagram, the lie detection machine, the lie detector. What the lie detector is doing, it is identifying truthful people 88.9% of the time. So you're going to notice right here, the 80% of people that are truthful, the lie detector is going to say they are telling the truth 0.889 or 88.9% of the time. You're going to notice the word negative is right here. In this instance, right here in purple, a positive test is one where the person is a liar, but they were truthful. So that means if it says negative right here, that means it is a false positive, that the person is actually telling the truth. So that is a negative result on the lie detector test. Whereas if it says a positive result from the lie detector, that means it is saying the person was a liar. Positive means they were a liar. But what you are noticing in the first branch of this tree diagram is what it referred to as a false positive. This person was not a liar. They are part of the truthful category. So we are assuming they are a truthful person. Therefore, if the lie detector says they are a liar, that is a positive result because that's what positivity means in this case. But the way you would calculate that probability anyway is you would just do 100% minus the 88.9% that it gave us right there, and that's where 0.111 would come from. So that is the complement of that situation. The other branch of the tree diagram is the 20% of the population that was a liar. If the lie detector test is correct on identifying liars 75.6% of the time, then that means if they are a liar, then 75.6% of the time, it is a positive result. They were a liar. And then right below that, you have the false positive, 0.244% chance that they are, according to the lie detector test, a truthful person when in fact they are a liar. At the very least, look at where all the numbers are. Look at where they go. I know this question kind of has some double negative, opposite logic with the whole false positive idea, but at the very least, something to just take away from it. Every branch is going to add up to 100%, and the initial branch also has to add up to 100%. The rest of the problem moves as follows. A randomly selected person from the population tests positive for being a liar. What's the probability that they are a liar? So you need to calculate that. We have, of the 80% of people who are truthful, about 11% of them are being labeled as a liar by the lie detection machine. So you have to do 0.8 times 0.111. That's just the people who were truthful that the lie detector said were liars. You have to add that probability to the people who were actually liars and the machine confirmed they were liars. So that's where the 0.2 multiplied by 0.756 part comes into play. And that would make up your denominator when you add those two things together, and that would give you 0.24 in the denominator. The probability that somebody is actually a liar, then that means they would be in the liar category, and then they test positive for being a liar. So you would multiply 0.2 and 0.756, and that would go in the numerator. Number 15, the first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine, approximately 5% of normal pregnancies will receive a positive result. If 100 women with normal pregnancies are tested with the first trimester screen, what is the probability that at least one woman will receive a positive result? This is a question asking you to do the at least problem. A very good problem that has been talked about in class where you should absolutely pause this video and try to do it on your own before looking at the answer. But here we go. If there is a 5% chance of the pregnancy being normal, there is a 95% chance of it being, or of the getting a positive, or if there's a 5% chance that a normal pregnancy is getting a positive result, then there is a 95% chance that it's getting a negative result. And we are trying to see out of 100 women, the probability of at least one woman receiving a positive result. So the way you do that is the probability of at least one event happening means take 100% and subtract the probability that the event does not happen at all. And the likelihood of this event not happening at all would be when you take 0.95, because that is the chance for getting a negative result, and you multiply that by 0.95 100 times. So you could do 0.95 to the 100th power. That would be the odds of getting 100 tests in a row that are all false positives, that are all giving you that negative result. And when you do that calculation, you get 0.0059, subtract that from 100, and you are left with 0.9941. There's a 99% chance that out of 100 women, one of them is going to have a positive result for the first trimester chromosomal abnormalities. Last part, if A and B are independent mutually exclusive events, the probability that A and B both occur is multiplying the probabilities together. We already kind of talked about this with independent events. You just multiply the things together. In number 16, Miss Raines decides to give her AP Statistics class a pop quiz with 4 multiple choice questions. Each multiple choice question has 5 possible answer choices. What is the likelihood of guessing correct on all 4 questions? That means there is a 1 out of 5 chance of guessing correctly on number 1, and then you have independently another 1 out of 5 chance of guessing correctly on problem 2. And then you would multiply those fractions together 2 more times for the likelihood of you guessing correctly on all 4 of the questions, which is the same thing as doing a 1 out of 5 to the power of 4, which is less than 1% chance. You have a very, very low chance of guessing all 4 questions correct on a 5 multiple choice question test. One more. This is just a conceptual question, a good one to pause and read, and basically you're just saying yes or no if this makes sense. In the United States, 28% of the population has hair that is blonde. A couple in the United States is expecting quadruplets. Does this mean there is a 0.28 times 0.28 times 0.28 times 0.28 probability that the quadruplets will have all hair that is blonde? Explain. And that is not correct at all. Each kid's hair color is not independent of the other kid's hair color. All the kids are coming from the same married couple or the same family. They share genetics. So if one kid is blonde, it is now very predictable that their genetics are going to be in a sibling's genetics and that they're going to have blonde hair as well. So that is just conceptually understanding likelihood of independent and dependent events. Hope this video helped you understand conditional probability and that we looked at some good examples. I will see you next time.